Hello students, I am Dr. NAVNEET KAUR, Associate Professor in Department of Electronics and Communication Engineering, Saga Institute of Research and Technology College. Today I'll be taking my next lecture on subject signals and systems. The topic which I'll be discussing here is the convolution of the signals. Now, first thing that any discrete time signal can be represented using impulses. Now say if I have any discrete time sequence xn, which is having sample at n is equal to 0, 1, 2, 3, -1, -2 as shown in the diagram. Now, I can represent it as a sum of weighted and shifted impulses. That means I can represent the sample which is at n is equal to 0 as x0 delta n, where delta n represent a unit impulse which is located at n is equal to 0. Since we know that the strength of the unit impulse function is 1, so this product will give only the value of the sample x0. Similarly, the sample at x1 will be represented as x1 into delta n minus 1, where delta n minus 1 is the shifted impulse at n is equal to 1. And now if I want to represent sample at n is equal to -1, I'll say x minus 1 multiplied by delta n plus 1, where delta n plus 1 is the shifted impulse at n is equal to -1. Similarly, at n is equal to 2, I'll multiply the sample value by delta n minus 2 and so on. And I'll sum all these values, and this is how my sequence xn will be represented as sum of x0 delta n, x1 delta n minus 1, x of -1 delta n plus 1, and so on. Now, talking about the response of a discrete time LTI system. Now, suppose if I have any discrete time, linear time invariant system, now I'm giving xn as an input signal to this system. I will get output signal as yn, which is also called the response of the system. Now, this Hn is known as the unit impulse response of this discrete time LTI system. Unit impulse response means that this is equal to the response of the system when the input is given as unit impulse function. Now here, I can represent this statement by this function. When delta n, it corresponds to Hn, when delta n minus k also corresponds to Hn minus k. This property holds because the system is linear time invariant. Now, time invariance property says that the delay in time does not make change in the signal. So if input delta n is given and the output is Hn, and if I'll shift delta n by k units, then output will also be shifted by k unit. Now, using the principle of linearity, xn, now I can represent it as xk delta n minus k, which I have discussed in my previous slide, that I can represent any signal as the sum of the weighted and shifted impulses. Now, if I want to find out yn of the system, yn will be, it will be the operator which will be acting upon this whole right-hand side term. Now, when h will be operating upon delta n minus k, I will take xk as out because it is independent of n. Now, when h will be operated on delta n minus k, I'll get hn minus k. So, now the output will be summation xk h n minus k, which is the formula for the convolution of xn and hn, and it is represented as xn convolution operator and hn. So, if I want to find out output of any discrete time LTI system, I will take the convolution sum of the input signal and the unit impulse response of the system. Now, output of any DT-LTI, discrete time LTI system, is represented by this formula, summation xk hn minus k, which is given as xn convolution operator hn. Now, we will see one example where we are calculating the convolution of the two sequences Hn and Xn. Now say Hn is represented by 1, 2, -1, -1, where the sample value in red represent that it is at n is equal to 0. Now, if it is at n is equal to 0, this sample will be at n is equal to -1. This will be at n is equal to -2. And this sample will be at n is equal to 1. Similarly, Xn is represented by this sequence. Now, since it is shown in red color, that means this is the sample at n is equal to 0. So, this will be the sample at n is equal to -1. And this will be at 1 and 2. Now, this is shown graphically also. So, the sequence representation will be clear with this waveform. Now, when we are finding the convolution of the sequences, first thing which we want to calculate is how many samples will be there in the linear convolution. Now, always remember that the number of the samples in the linear convolution is capital L plus M minus 1, where capital L is the number of the sequence in first sequence, capital M is the number of the samples in the second sequence. So, now the formula says that it should be L plus M minus 1, or I can say Lx plus Lh minus 1. Now we can see that in my first sequence, there are 4 samples. In my second sequence, there are also 4 samples. So according to the formula, in convolution, there will be 4 plus 4 minus 1. That means there will be 7 samples. Now I will calculate the number of the samples in convolution sum. Now, for that, one more thing which I need to know, that how many samples will be there on the left hand side of n is equal to 0 and how many samples will be there on the right hand side of the n is equal to 0. Now, if number of samples on left hand side of first sequence is say L, and in number of the samples in second sequence is say M, then the number of the samples in the convolution sum on the left hand side will be L plus M. Now we can see that here the number of samples on the left hand side in first sequence is 2 and in second sequence is 1. Now in convolution samples, there will be 3 samples on the left hand side. That is y minus 1, y minus 2, y minus 3. Similarly, for right hand side, I'll again sum up the number of the samples on the right hand side of the both sequences. Now in first sequence, there is only 1 sample on the right hand side, and in second sequence, there is only 2 samples in the right hand side. So the total number of the samples in right hand side will be 3. So 3 means y1, y2 and y3. So since there are 3 samples on left hand side, 3 samples on the right hand side, and 1 sample at n is equal to 0. So total samples will be 7, which we have already calculated. So we will start with y minus 3, then we'll calculate y minus 2, y minus 1, y0. Then we will calculate y1, y2 and y3. Now using the formula which we have already given, yn is equal to xk hn minus k, I'll calculate the value of samples of convolution sum. Now suppose if I want to find out my first sample y of minus 3. Now here n is equal to minus 3. I will keep n here as minus 3. So yn will be given as xkh minus 3 minus k. Now I'll keep on putting values of k and I'll sum up all those values. Like if I'll put k is equal to 0, I'll get x0, h of minus 3. So I'll take x of 0 here as 0 and h of minus 3 here is 0. So 0 into 0 will be 0. So I'll keep on changing the value of k from minus infinity to infinity. That means I'll take out the values of k for the number of the samples which are present. And I'll take out the value which will be 0. Similarly, using the formula, I'll put n is equal to minus 2 for y minus 2. Again, if I'll calculate, I'll get value 0. Now for y minus 1, when I'll calculate the samples, it will be 1. For y0, it will be 2. Y1, it will be minus 2. Y2, it will be minus 2. Y3, it will be 1. And for y4, it will be 1. So this is how I'll calculate the convolution sum. Now, there are some examples of the discrete time convolution. Now, first example is if I want to calculate the convolution of the unit impulse. Now, if signal is delta n, yn will be given as xk, h delta n minus k. Now, according to the shifting property of the convolution, according to the shifting property of the unit impulse function, if I'll multiply any signal with the shifted impulse signal, I will get the signal itself, which is located at the point where this impulse is located. Now, here, the signal is located at xk. That means time variable is k. That means here now delta is shifted at n. So I will get this signal x, which will be located at n. Similarly, I want to find out for hn is equal to un. Now xk un minus k, when I'll calculate, I'll get this expression. Similarly, I can take for delayed unit impulse. Now we know that when I am taking convolution of xn and delta n, I'll get xn. Similarly, when I am taking convolution of xn and delta n minus 0, I'll get xn but shifted at n0. Similarly, for integration, when hn is a raised to power n un, I will get yn as this expression. When n is equal to 0, it is having value 1. And when n is greater than 0, it is 1 minus a n plus 1 upon 1 minus a, where a is the common ratio and n is the number of the terms. Now, coming to the properties of convolution. The convolution sum is commutative. That is, x convolved with h will give h convolved with x. Similarly, it is distributed. That is, when xn is convolved with h1n plus h2n, it will be same as xn convolution h1n plus xn convolution with h2n. That means if I put it in the block diagram form, if xn is given to the system which is having unit impulse response h1n plus h2n, I'll get yn. Now coming to the right hand side, it will be drawn as this system is separated as two systems, each having unit impulse response h1 and h2 respectively. Now that means if the unit impulse response of the two systems are added, that means the two systems are placed in parallel. Similarly, for associative property, now I'll take it as xn in convolution with h1n in convolution with h2n. It will be same as xn when convolved with the convolution sum of these two systems, and output will be generated. That means if two systems are in parallel, their unit impulse response will give as the unit impulse response, which will be the convolution sum of these two impulse responses. Now, for continuous time signals, there is a slight change in the formula for the convolution. Now, if I am having two continuous time signals xt and ht, then according to the definition of the convolution integral of two continuous signal, yt will be given as minus infinity to infinity x tau ht minus tau d tau, where tau is the time variable. And x and h are the two signals of which the convolution sum is desired. Now, for computing the convolution of two continuous time signals, we will plot x tau and ht minus tau. Now, we will take different values for t, and we will take the shifted version of ht minus tau, and we will take the product of x tau and ht minus tau, and we will find out the value for yt. And the example for this convolution of two continuous time signal will be taken in my next lecture. But as per now, we should remember the formulas for convolution sum of discrete time signals as well as continuous time signals. Thank you. This is all for today's lecture.